Bismillahirrahmanirrahim. Assalamu alaikum ji. Today we will start with logistic regression. It is an algorithm we use to carry out classification. Its name is misleading because we are using regression to refer to this algorithm, but in fact we use it for classification. We will build this classifier using regression, and that's why we call it logistic regression. Our outline for the next couple of videos would be that we will start with logistic regression, a mathematical framework or mathematical model for logistic regression, and then we will talk about the decision boundaries for a logistic regression classifier we have in the feature space. How can we formulate loss function which we should optimize to find the parameters of logistic regression model, and then we will employ gradient descent to solve this optimization problem or for the optimization of the cost function. And finally, we will conclude this topic with multi-class logistic regression. We start with a recap of classification problem. In classification problem, we have this dataset D in which we have n training instances, x1, y1, x2, y2, xn, yn. This x1, x2, xn, these are the input features, and y1, y2, yn are the associated labels with each training input. And we assume that each of the input belongs to d-dimensional feature space, and each of the label belongs to this class y. And depending on the size of this y, we categorize classification into broadly two categories: binary or binomial classification, or multi-class or multinomial classification. For binary classification, this y can only take two values. Y can be 0, 1, or it can be -1 or 1. Applications of binary classification includes disease detection. It could be spam email classification, fraudulent transaction detection, or win-loss prediction, and so on and so forth. For multi-class classification, in this set y, we can have m values, or y can take any of these m values, or we say we have m classes. For a given training input, we want to build a classifier that can predict, that can assign label to the input, and that label can take any values from 1, 2, 3 to m. Applications of multi-class classification includes emotion detection, or it could be you want to classify vehicle type, make, model from the images streamed by road cameras. Given a speed signal, you want to identify a speaker. This is again a multi-class classification. Or it could be sentiment analysis from the image, text analysis, or it could be you take an image of the sky and you determine the pollution level, whether it is healthy, moderate, or hazard. Again, so all of these are examples of multi-class classification. This was a recap of the classification. Let's start with logistic regression. When we talk about classification tasks, we studied one algorithm in the very beginning of the course, and that was k nearest neighbor. K nearest neighbor was instance space classifier. And then we studied recently a naive Bayes classifier, which belongs to the class of generative classifier. In naive Bayes, we indirectly compute probability of y given x, posterior probability, as likelihood times prior, and we simply use Bayes rule to relate these two probabilities. Now we talk about logistic regression. So logistic regression belongs to the class of classifiers which are called discriminative classifiers. So we call these classifiers as discriminative because we estimate probability of y given x directly from the data. In generative classifiers, we indirectly computed this probability, but in discriminative classifiers, we estimate probability of y given x, probability of having a label y given x directly from the data. Right? So logistic regression, as I said earlier, is an algorithm to carry out classification. Its name is misleading. The word regression is due to the fact that the method attempts to fit a linear model in the feature space. And we will see this very shortly, that we use regression to fit a linear model, and then we will do something. We'll impose some mapping on the linear function to make it classification. So instead of creating a class, we compute the probability of instance being that class. Mathematically, it simply means that we want to define a model in logistic regression that is characterized by some variables theta, and we compute probability. Hypothesis function would depend on these parameters, and it takes an input x and it computes the probability of having a label y given x, and we know we call it posterior probability. So this is a very simple mathematical characterization of a parametric classifier or a discriminative classifier. Logistic regression model is a simple form of a neural network, because I wanted to mention this before we move forward, because we will build a neural network using the concepts of logistic regression. If you understand logistic regression, it will be very easy to follow the construction of neural networks. Let's build a model of logistic regression classifier. We consider a binary classification problem, and we will consider a binary case for most of the time in studying this logistic regression. We assume that we have a multi-dimensional feature space. Each of input has d features, and these features can be categorical variable, for example, gender, ethnicity, sentiment, or it can take continuous values or real values, or for example, height of mountains or temperature in a city, and so on and so forth. Okay, what is logistic regression model we have? As the name suggests, it's a sort of regression, right? Okay, let's build this model. We assume that input we have x1, x2, xd, so d number of features at input, and we also add one constant feature, and that does not depend on the input, right? It is just a constant, and we will see very shortly what's the interpretation of this constant. We multiply each of these inputs with some variables which are called parameters of the model, theta 0, theta 1, theta 2, theta d. So from here onwards, we have the model for logistic regression. So 1 will be multiplied by theta 0, the first feature will multiply theta 1, second would be theta 2, and ith feature would be multiplied by theta I. Right? And then we simply sum theta naught plus x1 theta 1 plus x2 theta 2, and so on and so forth. When we sum all of these, we get a linear sum of this. We have theta naught plus theta transpose x. And if you try to interpret this h of theta x, so it depends on theta, it takes an input x and it gives you a scalar value. So it's a mapping from d-dimensional space to R. So x is in the d-dimensional space, and what we're getting is a scalar. Now you can understand what do we mean by theta naught here, and why did we add this one here. And this one was added simply to represent bias in this linear model. So we have seen this before, right? This is nothing but just a linear regression model. A weighted sum of input features plus bias, right? So this is in fact regression, and what we're getting here is a real valid output. Hang on, we wanted to build a classifier, right? So far this is very similar to regression. How can we carry out classification when we have h theta of x? we can build a very simple binary classifier, right? So we can learn these parameters theta 1, theta 2, theta d, and theta naught, such that when we have class 1, this weighted sum is greater than 0, and when we have class 0 label, this weighted sum is less than equal to 0. Right? But if we follow this, h of theta of x can take any value from minus infinity to infinity. When it takes value from 0, okay, slightly greater than 0 to infinity, we assign a label to the classifier as 1, and when it is from minus infinity to limiting 0, we say classifier takes a value 0, right? But we wanted probabilities instead, right? So we want to find out posterior probability. What is the probability that y given x? And we know that probabilities are between 0 and 1. How can we transform, or how can we map this real value how can we squeeze this real value between 0 and 1? To do this, we use a function, what we call logistic function, or we call it sigmoid function, which is mathematically given by 1 over 1 plus exponent of negative of the input. It's a mapping from one-dimensional space to one-dimensional space, or it takes a value from minus infinity to infinity. Z can take any value from minus infinity to infinity, and what you get is a value between 0 and 1. So in general, we refer to this function as an activation function. Logistic or sigmoid function is one type of activation function, and we will see when we study neural networks that we can have different choices of activation functions. If we stick with logistic for now, for sigmoid function for now, we get this classifier. So at the input of classifier, we have values from minus infinity to infinity. At the output of sigmoid, we have values from between 0 and 1. So sigmoid is simply mapping the real values, a weighted sum of the inputs plus bias, into probability. Right. So this is in fact what a logistic classifier is. It is a weighted sum of inputs, and you pass the weighted sum through a sigmoid function, through a logistic function, and what you get is a probability in a value between 0 and 1. Okay, let's talk about this logistic function in more detail. Right? Let's try to understand this logistic function and why do we call it sigmoid function. This function is given by this plot. It's a mapping from one-dimensional real space that can take any value from minus infinity to infinity, but it returns you a value. So y-axis is between 0 and 1, right? And if you note this plot, if you observe this plot, when z is less than 0, right, it returns you a value less than 0.5, between 0 and 0.5. And for z greater than 0, we get a value greater than 0.5. When z is equal to 0, we get exactly 0.5. Right? So what is the interpretation? It maps, logistic function maps minus infinity to infinity, the real domain, to it squishes the whole real domain between 0 and 1. Right? It is monotonically increasing. It squishes value, from minus infinity to infinity to 0, 1. And one good thing about this sigmoid function, this logistic function, that it is differentiable. And this is something, and this is a property most of the times we would like to have, because this will help us in learning the parameters by employing gradient descent. Recall, when we compute the step of a gradient descent, we are required to take derivative. And this having a model that is differentiable uh, gives us a flexibility that we can employ gradient descent to learn the parameters. We call this function as logistic function, but this is in fact a simplified form of a generalized logistic function, which is given by three parameters: capital L, which is the maximum value a function can take, minimum value is 0, L is the maximum value, K quantifies the stupidness of this logistic regression function, and Z naught is the center. When I substitute K is equal to 1, Z naught is equal to 0, and L is equal to 1, we recover a standard or a simplified logistic function. We call this function as sigmoid function because of an S-shaped curve. If you see the plot of this curve, it is S-shaped, and therefore we refer to this logistic function as sigmoid function. Right? So far we have talked about logistic regression model, and now we have a good understanding of this logistic function. So this is the model we discussed. I'm going to slightly change the notation for mathematical convenience, because this will help us in having a more compact representation or more elegant representation of the formulation. So previously we said x1, x2, xd as x, but now from now onwards, when we say x, we will also include this 1 here. So x belongs to rd plus 1. Similarly, theta would include theta 0, theta 1, theta 2, theta d. Theta also belongs to d plus 1 real space. Right? And so we sum, we multiply 1 with theta naught, x1 with theta 1, and we sum. What we get here is simply an inner product of theta and x. So this is theta transpose x, and to be very precise, it should be a mapping from rd. In fact, it is from rd to r, because 1 is just a constant, right? But if you want to take it as rd plus 1, that is an equivalent representation, right? And then you pass this inner product, this weighted sum, through logistic function, and what we get is final form of our hypothesis function h theta of x, right? Okay, so from this slide onwards, we will stick to this notation. Input x contains features n1, and theta would the parameters are for a d-dimensional feature space, we have d plus 1 parameters. Okay, given the logistic regression model, how can we carry out classification? We assume that the model is given to us, and we know these parameters theta 0, theta 1, theta d. And how can we assign label to any input x? To answer this, we first need to understand that what does this h theta of x represent? So this represents the probability of class membership. It quantifies what is the probability that a label is 1 given x. It assigns class by applying threshold. So for any input x, we compute this probability, and if this h theta of x, this sigma of theta transpose x, is greater than 0.5, we would assign y hat a label class 1. Otherwise, we will assign 0 to y hat. So here we have used 0.5 as threshold, or we can say 0.5 with a threshold that is defining the decision boundary. If the output is greater than 0.5, you would consider input in class 1, otherwise you treat input in class 0. And we will see that we can also use values other than 0.5 as threshold. So one more interpretation of logistic regression we know that probability of y is equal to 1 given x is h theta of x. If I ask you what is probability of y is equal to 0 given x, that would be 1 minus h theta of x. And if you simply do some algebraic manipulation, you can write this as 1 minus h of theta in this form. The odds in probability, the odds in favor of an event with probability is p over 1 minus p, right? So what is odd? In probability measure, that probability is between 0 and 1, but odd would be between 0 and infinity. When probability is 0, odd is 0. When probability is 1, odd would be infinity, right? So if we use the concept of odds in favor of an event, and if we define odds of class 1, we simply take a ratio of probability of y is equal to 1 given x divided by probability 1 minus probability of y is equal to 1 given x, which is in fact probability of y is equal to 0 given x. So this is odds for class 1. We take a ratio of these two, and what we get is this. And if we take log of this, we obtain so log of this factor. When you move this in the numerator, you add a negative sign outside the log, and then log of exponent of minus theta x would be simply minus theta transpose x, and what you get is theta transpose x. How do you interpret this? We can say logistic regression considers log odds as a linear function of x, or simply logistic regression is a linear classifier of log of odds. This is another way to interpret logistic regression, right? Like we have probabilities, we convert this into odds, and we take log of odds, and that is a logistic regression classifier. Right, let's consider one example in which we will use logistic regression to predict disease. So the problem is that we want to diagnose cancer given size of the tumor. So we assume and we only have one scalar input, tumor size, which is x. We have binary output, y is equal to 0 if tumor is benign, and y is equal to 1 if tumor is malignant. And if we simply use linear regression model, that will be simply given by theta naught bias plus theta 1x. And the issue with this is that output is real valued. To squish the value between 0 and 1, we pass this linear model through sigmoid, and what we get is 1 over 1 plus exponent negative of the linear model. So it squishes values from minus infinity to infinity to 0 and 1, right? So if we have this regression model, and for any input x, if you're given that h theta of x is 0.65 for any tumor size x, so how would you assign class label to this x, right? We say the probability is 0.65. And what we said earlier, that h theta of x quantifies probability y is equal to 1 given x. Since this is greater than 0.5, so we can say the tumor is malignant, or we can diagnose cancer for this given size of a tumor, right? So that's all about the model of logistic regression. If we summarize, logistic regression is simply you carry out regression, a weighted sum of the features plus bias, and you pass this weighted sum through a sigmoid function to map to get the value between 0 and 1. Right. So in the next video, we'll talk about decision boundaries of our logistic regression classifier. We stop here, and we will see you in the next module, inshallah.